frequency stability is of the utmost importance. As an example, let's consider a radio broadcast station. One particular regulation prohibits the frequency of the station from changing more than a few cycles, so that the station will not interfere with another station operating on a nearby frequency. Now, for this reason, the oscillator producing this frequency must be one with the very best frequency stability. An oscillator capable of producing such an output is the crystal-controlled oscillator. We're not going to study the oscillator circuit in this lesson, but we will study the characteristics of the crystals used in such a circuit. And here I might add that the crystal will be used as the frequency determining device of the oscillator. A crystal used in oscillator circuits must possess a characteristic known as piezoelectricity, or the piezoelectric effect. Now, the piezoelectric effect is defined as the property of a crystal by which mechanical stress produces electric charges, and conversely, electric charges produce mechanical stresses. Now, this is saying nothing more than if a voltage is applied to the crystal, it will vibrate. The amplitude of these vibrations are much greater at one frequency than at any other frequency. Now, this one particular frequency is called the natural resonant frequency of the crystal. Now, let's look at some of the crystal substances that possess the piezoelectric characteristics. They are Rochelle salt, tourmaline, and quartz. Now, of these three, Rochelle salt exhibits the piezoelectric effect to the greatest degree. However, quartz crystal is most generally used because it has a greater mechanical strength. Quartz crystal, remember, it has a greater mechanical strength. Now, I want to show you a piece of quartz crystal in its natural form. Now, if we were to examine this carefully, we can see that the quartz crystal has a hexagonal cross-section. That is to say, it has 6 sides. Now, also, quartz crystal in its natural form has pointed ends. Now, let's take a look at this drawing so that we can determine more about the quartz crystal. The top viewed indeed shows us that the quartz crystal has a hexagon shape, 6 sides, while the lower view points out that indeed the quartz crystal in its natural form does have pointed ends. Now, quartz crystal in its natural form cannot possibly be used in oscillator circuits. It must be cut in a specific manner to exhibit its piezoelectric properties. I know all of you at one time or another have heard of diamond cutting. The reason the diamond is cut is to give it brilliance, and the manner in which it's cut will determine its degree of brilliance. Now, all crystals are not cut in exactly the same manner, just as all diamonds are not cut exactly the same. The properties which a crystal exhibits are dependent on the manner in which it's cut. Now, there are many different cuts, but we're only going to examine 3 basic cuts. Let's go over, and I want to show you the actual cuts now. I have here 3 crystal cuts. Now, all crystals look the same, but not all will exhibit the same characteristics. Its frequency will be dependent upon its thickness. Let's take a look at 2 pieces of crystal cuts and compare this difference in thicknesses. As you can see, the thinner cut here, the thicker cut here. We're indicating here that the vibration of this thinner cut, or the frequency, is greater than this cut. Now, this will always hold true. The thinner the crystal cut, the higher the frequency of oscillation. Now, there are a few other crystal cuts with better frequency stability, but these will not be discussed in this lesson. Now, when an extremely high degree of frequency stability must be maintained, the crystal will be placed in a temperature oven. A temperature oven is nothing more than a thermostatically controlled container used to maintain the crystal temperature in its proper range. And in doing so, of course, we have a high degree of frequency stability. Now, in order for a crystal to be used in an oscillator circuit, it first must be placed in a holder. Now, the crystal holder will support the crystal physically and provide the electrodes by which this voltage is applied to the electrode. The holder must allow the crystal maximum freedom of vibration at all times. Let's look at this drawing of a typical holder. The crystal will be placed in the holder between two parallel plates. The plates have an air gap between them, which allows room for the crystal to vibrate. Now, these are the pins that will allow the voltage to be applied to the plate. And also, the pins will allow the crystal to be connected into a circuit. Now, so far, we've seen the physical characteristics of the crystal. Let's now see how the crystal reacts electrically. To do this, we'll look at the electrical equivalent of a crystal and its holder. The crystal itself, when vibrating, acts very similar to a series resonance circuit containing resistance, inductance, and capacitance. Remember, this is when the crystal is vibrating. Now, when the crystal is placed in the holder, the capacitance of the holder will be placed in parallel like this. CH, the capacitance of the holder. So this capacitance represents the holder capacitance. This represents the vibrating crystal. Now, just because this vibrating crystal is equivalent to, or is the equivalent of a series LC tank circuit, I don't want you to think that it's the same thing, because the crystal will be far superior to the LC tank circuit. Now, the Q of the crystal circuit is many times greater than that of the LC circuit. Let's take a look at the comparison between the Q of a crystal and an ordinary LC tank circuit. The Q of an LC tank circuit is seldom greater than 2,000, whereas the Q of the crystal is sometimes as great as 30,000. And as comparing these two, you can see that the Q of the crystal would be many times greater than that of the LC tank circuit. Now, because of the high Q, this would mean that the crystal would have better frequency stability. Now, let's look at some of the values, both physical and electrical, of a typical crystal. Since the crystal is going to be used in an oscillator circuit as the frequency determining device, let's take a look then at the schematic symbol for our crystal. These two plates represent the crystal holder, while this area would represent the crystal itself. Now, this is the schematic symbol of a crystal used in oscillator circuits.